Hi everyone, I'm Cheryl. In this problem, we're giving a lamina that's bounded by y equals 4 minus x squared, y equals 0, and I know that x is greater than 0. I have a picture of that region on the board. I also know that I have a density function, rho of xy equals k times x. I'm asked to find 5 different things in this problem. First of all, we'll be looking at the moment of inertia about the x-axis. Secondly, the moment of inertia about the y-axis, the polar moment, and then we'll be looking at the radius of gyration with respect to the x and the y-axis. So let's begin by looking at that moment of inertia about the x-axis. Now I know that for a fixed mass, that inertia is the mass times the square of the distance. But in this case, I don't have a constant mass, so I'm going to use my double integral. So my moment of inertia about the x-axis can be calculated by the double integral across a region of the square of the distance to the x-axis. So that'll be y squared times my density function, dA. All right, so I've got y squared. Rho is going to be k times x in this particular case. And now I have to decide how I'm going to integrate, whether I start with the x and then integrate with respect to y or vice versa. So let's come over here and look at my lamina. I think I'm going to set this up using a vertically simple piece. So again, I'm going to take my change in y first. So this will be dy dx. Once I've made that decision, I know what my limits of integration are going to be. I'll start from 0 and go up to this curve. So I'm going to go from 0, and the curve is 4 minus x squared. Then I'll be moving from 0 to 2 for my outer limit. Okay, now that I have my integral set up, I'm going to begin by looking at the inside integral. Now remember, y is the variable of integration, so I'm going to be treating x as if it's a constant. So the k and the x are constant multiples that can be pulled out, and integrating y squared, I get y cubed divided by 3. And I'll evaluate that from 0 to 4 minus x squared dx. Plugging in my upper limit, I'm going to have kx all over 3 times 4 minus x squared, that quantity, to the third power. Then I have to subtract what happens when I plug 0 in for y, but that's just a 0. So now I'm ready to work on my outside integral. Now if you look at this, you may notice that it's going to require a u substitution. But I'm going to go ahead and try to do that without writing out the details. I'm going to have a k over 3 as my constant that gets pulled out. And with the u substitution, I'll have a constant of minus 1/2, and this will become 4 minus x squared to the 4th all over 4. And then I need to evaluate from 0 to 2. I notice that I have a minus k all over 3 times 2 times 4, so that's 24 as a constant. And now we're going to plug our upper limit of integration into 4 minus x squared to the 4th power. Well, when x equals 2, this will be 4 minus 4, which is 0 to the 4th power. That's just 0. Now I need to subtract what happens when I plug in my lower limit of 0. So if I plug 0 in here, I will have 4 minus 0 to the 4th, which is 4 to the 4th, or 256. So this gives me a positive 256k all over 24, which reduces down to 32k all over 3. That is my moment of inertia about the x-axis. So 32k all over 3. Now we need to find the moment of inertia about the y-axis. So again, inertia for a fixed mass is going to be the distance squared times the mass. Because my mass is not fixed, I'll use the integral over the region. Now my distance squared, the distance from the y-axis, can be represented by x squared. And then I'll have my density function, dA. Okay, so here's x squared, and my density function is k times x. I'm going to choose the dA the same way I did in the previous part, so I'll do a dy dx, which means my limits of integration are the same. I'll be going from 0 to 4 minus x squared, and from 0 to 2. Simplifying that integrand a little bit, I'm going to have kx cubed dy dx. And I'll begin using the inside integral. So I've got the integral from 0 to 2. Y is going to be my variable of integration, so that means I treat x as if it's a constant. So the integral of kx cubed is going to be k x cubed y, evaluated from 0 to 4 minus x squared dx. So I've got my integral from 0 to 2. I'll plug in my upper limit, so I have kx cubed times the quantity, 4 minus x squared. Then I need to subtract what happens when I plug 0 in for y, but that just gives me 0. And I think on this one, I'm just going to distribute the kx cubed across. So I have the integral from 0 to 2 of 4k x cubed minus kx to the 5th dx. And integrating this, I'll have 4k x to the 4th all over 4 minus k x to the 6th all over 6. And I need to evaluate that from 0 to 2. Now I notice here that the 4's cancel. So plugging in my upper limit, I'll have k times 2 to the 4th. So that will be 16k. And then minus k times x to the 2 to the 6th. So that's 64 minus 64 over 6, which is going to be 32 all over 3 times k. And then I have to subtract what happens. So that's plugging in the upper limit. I have to subtract what happens when I plug in the lower limit, but when I plug 0 in, I just get 0 again. So getting a common denominator, I'll have 48k minus 32k all over 3, which gives me 16k all over 3, which means that my moment of inertia about the y-axis is 16k all over 3. All right. The next piece asked me to find the polar moment. The polar moment can be found by adding the moments of inertia with respect to x and y. So this is just 32k all over 3 plus 16k all over 3, which is 48k all over 3, which is 16k. All right, we've now completed the first 3 parts of the problem. We still need to look for the radius of gyration with respect to the x and the y axis. So I'm going to clear the board and we'll be right back. Now that we've made some more room, let's go ahead and continue the problem. The next thing we need to do are to find the radius of gyration with respect to the x and the y-axis. So let's begin with the radius of gyration about the y-axis. This can be defined as the square root of the moment of inertia about the y-axis all over the mass. And the radius of gyration about the x-axis is defined as the square root of the moment of inertia about the x-axis all over the mass. Now notice that in these two formulas, I've already calculated the moment of inertia about the y-axis and about the x-axis. But what I'm missing here is the mass. So I still need to do a double integral to help me calculate the mass. So we know that the mass is the integral over a region of your density function, dA. So my density function is kx, and I'm going to set up this double integral the same way I did the others. So I will do dy dx so that it is vertically simple, which means my limits of integration are the same as before. So I'll be going from 0 to 4 minus x squared and 0 to 2. Okay, working with the inside integral to begin with. I've got the integral from 0 to 2. I'll be treating x as if it's a constant, so this will be kxy evaluated from 0 to 4 minus x squared dx. Plugging in the upper limit, I have kx times the quantity 4 minus x squared. And when I substitute in the lower limit, I get 0. So I just subtract 0, and this is dx. I can go ahead and distribute across, and I have 4kx minus kx cubed dx. So that's going to give me, for my integral, 4k x squared divided by 2 minus kx to the fourth divided by 4. And that's all evaluated from 0 to 2. I notice that I can do a little simplifying here because 2 goes into 4 twice. Plugging in my upper limit, I'll have 2 squared, which is 4, times 2, which is 8. So I've got an 8k minus 2 to the fourth will be 16. 16 divided by 4 is 4, so I'll have minus 4k. And when I plug in my lower limit, because that lower limit is a 0, both of those terms become 0, so I'm subtracting 0. And my mass is going to be 4k. Now I have everything I need to get the radius of gyration. So let's go back to my formula. And my radius of gyration with respect to the y-axis is going to be the square root of the moment of inertia about the y-axis. So that's 16k all over 3 divided by the mass, which I now know is 4k. So with a little arithmetic, I have 16k all over 3 times 1 over 4k. The k's cancel. 4 goes into 16 4 times, and I have the square root of 4/3, which you can write as 2 over the square root of 3, which is perfectly fine. If you prefer, you can rationalize this and write it as 2 root 3 divided by 3. Okay, let's get the radius of gyration with respect to the x-axis. So I know it's the square root of the moment of inertia about the x-axis, which I've already calculated to be 32k divided by 3. But I have to divide that by the mass, which I now know is 4k. Again, a little arithmetic. and I have 32k all over 3 times 1 over 4k. The k's cancel. 4 goes into 32 8 times, and I have the square root of 8/3. And if you want, you can write this as 2 times the square root of 2 all over root 3. And if you want to rationalize this, you could write it as 2 root 6 all over 3. And that will give you your radius of gyration. I hope that was helpful. Thanks.